Thanks for joining us. Yeah, welcome to the workshop. My name is Carl Tape. I'm going to start things off on the project. We have a large team. I'll introduce everyone. I'll show you where all the content and slides are. As I mentioned, if you go to the workshop webpage, there's a link at the bottom that says workshop materials. It's a Google Drive with a few sets of slides. You can follow along. It'll be very useful for like copying and pasting commands during the workshop. So general picture will be having, the slides or Zoom, however you want, and then you'll have the container open. So there's kind of a lot to keep track of, but we'll launch off. So this is the opening slide, and we've got these. You can, once you're in here, these mean they're linked. So if you have the Google Doc open, you can redirect to different places. We want to thank the Air Force Research Laboratory as the principal sponsors for this project. These are a code we're using for research purposes. And we also have support from National Science Foundation from, in particular, Ian Wong collaborating to help make the containers for this project. The code here is featured as part of that project as well. So for now, we'll get to the Zoom things, but please mute yourselves for now, and we'll get to some other parts but regarding that. So these are the sort of host slides to kick off for day one. It's going to be probably like 15-minute to try to, no coding, just step into this topic. And then Julian Turin, a postdoc, will give a tour of the code, still no coding at that point, and then we launch into running things ourselves. So here we go. Just showing the personnel involved with this project. Julian Turin, Bryant Chow, postdocs, Amanda McPherson, PhD student, Becky Beltran on the sort of receiving end of the emails, and Akash Gupta, PhD student. These are folks contributing to the package, and Ian Wong, as I mentioned, helping with the container. This is a scoped project. If you type scoped seismology, you can see more information about that NSF project. Other team is from University of South Florida, Jochen Braunmiller, Glenn Thompson, Felix Cardozo, and then from Toronto, Chinya Liu, Liang Ding, and Gang Yang. And then Ryan Modrak from Los Alamos is the lead developer, did his postdoc up here at University of Alaska Fairbanks. And yeah, so there's some major contributors to the project. So the helpers today, the main people you might be interacting with are shown here: Julian, Bryant, Amanda, Felix, Liang. So, you'll see all of us, but if you see one of them, we hope they're able to help you out. Just want to sort of orient ourselves, or at least where I'm broadcasting from is right here in the center of Alaska. This is kind of one of my favorite views, just to give us a motivating shot of, if your interests are tectonic, here's one picture of the Earth. As I said here, that's where we are. You're all over the place, which is great. Just showing you a little more physical picture of where we are. This is where I am at this building right here. We're not in fall colors, where the snow is rapidly melting right now. But this just sort of shows you a picture of where we are physically, and, a bit of an ad for what we are here at UAF, and giving you an idea. We have a high performance computing. This is a satellite facility. You can see in the woods out here, there's a comprehensive test band treaty infrasound array. Within these woods back here, there's a GSN COLA station. I saw someone on here from the GSN network, so I'm glad to see that. And just giving you an idea of infrasound, volcanology research going on. There's a corner reflector for satellite. It's a cool place to do geophysics. We try to get our own students excited. So that's where we are physically. Wanted to go through some Zoom guidelines for the workshop. We want to interact with everyone, ensure a successful workshop. We want you to be engaged and ask questions. So here's some guidelines. So please display your full name, sort of like wearing a name tag in a workshop. If you need to change it so that we know who you are when we're interacting, that would be great. I'll show kind of how you can change your name quickly. Mute yourself unless you have a question. In the main room, we're asking to keep your camera off. We don't know about this bandwidth, but just to be sure, just keep your camera off in the main room, and raise your hand if you have a question. wait to be called on. You know, if things just go well, probably you can just unmute and speak up, but let's just try to go with that. Ask your host or helper if you need to share your screen, and this will be common in the breakout room. So we'll be sharing screens back and forth, but probably limited to the breakout rooms. If you're stuck, enter a breakout room that's empty. And if we see someone in there, we're going to try to find you. We have 5 of us. We're hoping there's not, tons of people. And just, with the chat, you can use the chat, but just be sensible. If you have something, we don't need thousands of chat messages or, socializing, I guess, either. But we'll try to get to those as well. And we'll have some poll questions like, are you ready to proceed, to help us gauge whether to move on? Just answer that. It's like, yes, no, not yet, almost, something like that. So here are the key buttons. I know most of you have been deep into Zoom or some other platform, but this is just the sort of key spots. There's the participants you can click on. You won't have the polls, but you'll have some polls popping up. There's breakout rooms to join and reactions to like raise your hand or lower your hand. So the chat, this is being recorded. Chat history will be saved. You have a lot of permissions here. We're not restrictive at all. We just trust that people will, use these fine. To mute or not, just mute yourself unless you're asked to speak. Share your video, as I said, and sharing screen mostly in the breakout rooms. And we're listed as host so-and-so. So if just to let you know who the sort of main hosts are. If you need to raise your hand, you can click reaction, raise hand. That would be preferred. If you can't figure that out, just unmute yourself and speak up. Well, that's not a problem. Same, lower your hand. If your hand doesn't get lowered, we think you still have a question. So you'll get a poll question. Are you ready to move on? Just answer that so we get a quick idea of whether to move on. And this is just to say, we're not waiting for the very last person. We're just trying to sort of get most people moving. As we say, we can go back to this stuff later and revisit the material. To rename yourself, you click participants, more, rename. So if you need to do that, that's shown there. And again, if I'm going too fast through these slides, you should be able to find these slides yourself and revisit them. Okay. We'll kick off with sort of introduction to seismic moment tensors. We're not just launching in and running things. We get some basic idea of moment tensors. Some of you are, deep into this topic. Some of you may not have seen this before, so we're going somewhere in between, but just saying, we see beach balls like this, a map of the GCMT catalog in Alaska. In this case, we're seeing colored by depth. We see a signature of a subducting plate going down and the kinds of mechanisms that tell us something about the style of faulting, like strike slip faulting in central Alaska, maybe thrust faulting from the 2021-22 magnitude 8 earthquakes out here. But this is just a motivation. We're aware of what these are and we're interested. How are these estimated? Why are we trying out a different code if there are beach balls like this already available from catalogs, for example? And the main point of this slide, which will be revisited later in much more detail, is just a picture to say we're seeking to find this beach ball representation of a source by calculating red synthetic seismograms shown here. For a given beach ball and a given structural model, we're trying to find the beach ball that fits the observed data the best. In this case, there's some body waves, there's some surface waves, Rayleigh waves on the vertical Rayleigh component, love waves. And the point here, these are 4 stations out of a lot of stations shown here at the left for some earthquake in Alaska at a certain depth. But the idea is we're looking at filtered seismic waveforms and we're searching over space of moment tensors where each beach ball gives a different set of red seismograms. And we're trying to find the red seismograms that fit the best and call that our best fitting moment tensor. In this case, it's a double couple. So seismic waveforms linked here. So here's the big picture goal, is that we're trying to find a moment tensor M whose synthetics provide the best fit to observed waveforms. So this would be like a search strategy would be to minimize this function by searching over all possible moment tensors. So this would be our synthetic seismogram for the ith component of the Rth station. And this would be the corresponding observed seismogram. So these will depend on the moment tensor chosen. We integrate squared over time, say like an L2 norm, and sum all these up. And so we're seeking to find the M that minimizes this function. The synthetic seismograms, and there's really not too many equations in here, but we need some equation that describes the synthetics and indicates the pieces that go into making the synthetic seismograms. So here we have a moment tensor. This is what will a 3x3 symmetric matrix with 6 unique entries. That's kind of what we're going for. And it can, the displacement field can be written as this convolution of a source time function with this sum over the components of the moment tensor multiplied by pre-computed Green's functions, which is impulsive response from a particular source at a particular time and based on an assumed velocity model. And so these are, the idea here is we pre-calculate some Green's functions, and we'll be doing this tomorrow for our own set, or we're accessing them today from Iris. And then once we pre-calculate them, we can rapidly create synthetic seismograms as we search over different moment tensors M. So this is the sort of setup where, in our case, we're really interested in this quantity right here. We're estimating this that describes the source. So here's our moment tensor. At the bottom is 3x3 matrix, symmetric. It has real eigenvalues. So just standard linear algebra, if we have a 3x3 matrix, we can write it as a combination of a rotation matrix that describes the orientation and the diagonal eigenvalues shown here. So these 3 eigenvalues of the 3x3 symmetric matrix give us the source type of the moment tensor, and this describes the orientation, like strike, dip, and rake. And these are the 6 parameters. Of the parameters we'll be searching over. We also have depth, for example. So just a picture of thinking about the moment tensor as slip on a fault. This shows, a fault plane. We have a north vector to give us some geographic orientation. We have the slip kind of from here. You can see the slip vector shown here. This would be a normal fault with a small strike slip component. Normal vector, slip vector, this would be the slip or rake angle. And this would be illustrating the moment tensor as a double couple. This would be the dip of the fault shown here. So this is a sort of common way that we look at these beach balls sort of geologically. We could go measure these geological faults and represent them if we have indications of slip by beach balls. And another common way in seismology is looking at the irradiation pattern. This is sort of a perspective, a view of that, where you have the color of the beach ball is related to the radial component of the wave field. So the P waves are sort of related to the P wave radiation. You have strong S radiation at these nodal lines where you see these tangential rays. This is also shown here for a double couple, another way of thinking about this moment tensor, different from the previous slide. So we think about the parameters to describe this. We can think of a block of orientation parameters, basically strike, dip, and rake angles. And so this brick represents the information that we would search over for in these moment tensors. So the orientation is described by strike, dip, and rake. And when we look at a parameter search, we can think of this as sort of a separate block for any given, say, moment tensor source type. The source type is shown here. So we have the orientation represented by capital U, and then the source type represented by the eigenvalues. Those 3 coordinates, which are real, give us a coordinate system, lambda 1, 2, and 3. And because we have a choice of how we can sort the eigenvalues, we just set them to say, this is going to be the biggest, this is the smallest. And once we set that, we don't need the full 3-dimensional space of eigenvalues. We just need this little loon. So this section, 1/6 section of the sphere gives us our coordinate space for source type. So there's nothing, we have the eigenvalues and now we're just plotting them. We conveniently kind of rotate things so that the 1, 1, 1 direction is pointing out the top and the -1, -1 direction is pointing out the bottom. So this would be an explosion. This one right in the middle, which is the coordinate 1, 0, -1, that would be the double couple at the center, and the implosion is at the bottom. And so that gives us, we'll be looking at a lot of these these football looking figures. And this gives us sort of like how we got there. It's just the eigenvalues normalized. The size, the norm of this would give us basically the moment or the magnitude. So we can think of 2 dimensions related to the source type, and the magnitude is a 3rd coordinate, and then there's 3 coordinates related to the orientation. So this just shows the picture that basically this loon divides the type of beach balls shown as all positive eigenvalues at the top, and then sort of white caps with red bands along this lambda 2 equals 0. You have crossing nodal lines. They're not necessarily 90 degrees. They can be all the way at any angle. And so that gives us the source types. And just wanted to sort of now say that uncertainties in moment tensor source type tend to be large. When we look at full moment tensors, this is from Ford and some study by Andrea Chang, they tend to be large, meaning it's really important to understand these uncertainties. When we go to make an interpretation, if we have very large uncertainties, we need to be aware of that. And that's part of the emphasis for what we're going to be showing in this workshop, is characterizing the variation of, say, your misfit function on the space of source type as shown in these examples here. This is just sort of a gallery of things to say. There's a lot of different ways to visualize these things. We're not showing everything, but we care about these because the uncertainties guide our ability to interpret processes. You know, which fault is active here? What's its orientation? Or make decisions like, is this an explosion or an earthquake? And so that motivates this sort of deeper dive into characterizing these estimated moment tensors. There's a lot of moment tensor codes out there. This is just a subset of some that to list here. You're probably familiar with some of these. Some of them are running operationally, like the TDMT code. So there's a landscape of materials out there that you should be aware of, and we are aware of, and we're also sort of help establish what we're trying to do that's either different, whether it's a framework or capabilities, or just establishing a more modular developable base. So you can revisit these. These links are all live if you want to from your Google Docs. Getting on to this workshop, basically these are some of the capabilities. We have columns, sort of what's available within the package. What are we actually doing within the workshop? We're not trying to illustrate everything. But fetching data from Iris, fetching synthetics from Iris, AxiSim, InstaSize, calculating local 1D synthetics using FK, moment tensor estimation with surface waves, body waves, first motion polarities, running on MPI with multiple processors, estimating moment tensor Green's functions, source side or receiver side. These are different strategies used, estimating a point source. These are things that are available in the package, and you get an idea of what's in this workshop. I also wanted to point out there are other things that have kind of in the development stage or being used with the code, but not necessarily right now available. And we'll revisit these in day 2, but that includes hypocenter, complex source time function, sort of search algorithms besides covering the whole parameter space, and sort of complete set of quantification tools for moment tensor uncertainty quantification. We aren't showcasing all these in the workshop, or using your own data and metadata. These are things sort of that are worth emphasizing, but will not be doing within this workshop. Okay, and a couple things just in terms of expectations to say that, you know, optimized speed of these runs is not a focus for us. We wanted to emphasize these Docker containers just to make sure things run. Docker containers, we found they don't necessarily all run at the exact same speed as if we were outside of Docker on some platforms. But we would rather have things work slow than not work at all. And for massive searches, we recommend, you know, in research mode, the code runs on, you know, hundreds of cores if you want to. It just depends on what resources you have. And also just saying publication level analyses, we're presenting examples as is. If we get some crummy waveform data, that's just what it is. We're not like hand picking and extracting things, but if you're going to do a publication on your own event, it takes a lot more time, as you can imagine. This is just showing some of the software that's coming in here. I need to add this which ref to put in here for OBSPI clearly, but this is we have sort of the latest versions of a lot of software: Python, OBSPI, InstaSize, GMT 6.3, FK, and then MTUQ. So just give you an idea of what you're going to be using and what's at your fingertips inside this container. A tip here is to follow along the workshop materials, revisit them later. This is one place you can find them. If you're in Google Slides, you can click here. You've already sort of been to that spot, but if you can't find this, you can find my website or find this page, click here, and you will land in this Google folder and find them. So that's one tip. And at that point, I'll stop here for this introduction and maybe just see if there's any quick questions about these materials. Sort of, we want to have a short break, but if there's any questions, you can raise your hand and ask them before we shift over to Julian to give the tour of the package. Sure. Go ahead, Christian.
Hey, well, I think I got the Docker installed, but I am not able to get onto Google Docs because of work security issues. Is this going to?
Yeah. Is that going to be an issue? No, I mean, you can manually type in the commands you'll be looking at, but it would be a lot easier. Maybe what we can try to do for that is to copy some commands into chat. We'll be showing the commands, but as you can imagine, it's easier to kind of copy paste than it would be to, yeah, to drop them in. I mean, you don't need a Google account or anything, but I can see that if someone restricts you from entering a public, it's open to the public, but I guess that capability can be restricted, it sounds. So thanks for asking, and we'll see what we can do in terms of dropping in some commands. There's a lot of commands to copy paste, so we are kind of counting on that access. So hopefully, yeah, if needed, you could run it after the fact. I would understand fully.
Yeah, I mean, even if you have like a slide pack that I can go through as almost like a tutorial, that's fine with me.
Okay, that would be accessed from any place you can get a public Google
any
link.
web page, like if you put it on your web page or something, that's perfectly okay.
Well, that's where everyone's finding it, though. It's through a web page in a publicly accessible file. So maybe I'll have to hear a little more about whether anyone else can't get there. Go ahead, Mao-Chun.
Hello, thank you. So you list a subset of moment tensor code.
Yes.
I'm wondering why there is no hash. I think hash is also
that's a great point. Yeah, we can add that there because it's a subset. Hash is not in that subset, but we'd be happy to list a larger set. It was just off the top of my head, but yeah, Harderbeck's shear code. We'll try to remember to add that. Yeah, feel free to, we can add more to that. It's good to be aware of that full landscape, especially before you dive in and consider something. Okay, well, no large list of questions here. So I think just moving things along, Julian, you want to take over and we're going to launch in and look at a tour.
Absolutely. So hello, everyone. Thanks for attending the workshop. So we don't have a dedicated website for the package. Everything is fine on GitHub. So you'll find it under the UAF GeoTools MTUQ repo. So currently we don't have a lot of users at the moment. We don't have a lot of stars and people watching the package, but I hope that after the workshop, we'll see this number grow because having people interested in the package using it makes it improve a lot because we're gonna have some hopefully bug hunting and other suggestions. So on this repo, you'll find all the source code. There's also a couple of examples that are bundled already in the Docker image that you've installed. And what I'd like to draw your attention to is on the README, we have a couple of links that will get you to the github.io page of the package, where you'll have all the installations instructions if you want to trying to install the package outside of the Docker container. So today we wanted to keep everything in Docker to maximize the chances of things working. But if you want to install it, we recommend using Conda for that. And then there's a couple of guides. So how do we acquire the data? How do we acquire the greens function? So that's the kind of stuff that you might want to do if you want to go further after the workshop. And there's also a visualization gallery where we can see the type of results that the code is doing for instance, force estimation, where instead of having the misfit on the loon, we will have the direction of the force pointing toward the bottom on the northwest direction. So we have that. We have a gallery of depth and location research, and everything related to plotting things on the loon. So it's not all about the misfit. We have different sort of visualization. We won't cover everything during the workshop, and we also probably going to have to add a couple of things here moving along. But I encourage you to check that. There's a couple of scripts to reproduce this image as well. So that's where most things are happening. So I will encourage you to follow what's happening on the MTUQ page if you're interested in following the evolution of the code. And with this, I think we can start going on the participants day 1. And I will give the floor to Felix.
So good morning to everybody. Thank you again for attending this workshop. So I'm going to jump to the content because Carl already explained all of this. So that's for reminding you, this is my colleagues and myself. So we are going to be leading today section. So if you have any doubt, hopefully we're going to be able to help you out in any doubt you have. So before we start with running MTUQ, it's important to be familiar with the Docker environment that we are going to use during the entire workshop. And the first concept that we need to have very clear is the concept of an image and a concept of a container. So if you follow the instructions that was sent to you a couple of days ago, maybe you already download the image, which is the file where it is containing all the programs, scripts, and everything that we are going to work with during the workshop. But in order to use this package or this environment, we need to run it, the image. So when we run the image in our local computer, we are going to create a container. So the container that I'm going to create with the image is going to be my container. It's going to be different than your container or other people's containers. So all of us are we going to create different containers from the same image, and the container is going to be the space where we are going to develop the entire workshop workflow. So at this point, you may already have downloaded Docker, and you already have downloaded the image after downloading Docker. So the first instruction for moving forward is please open a terminal in your computer. So it's in Windows or Mac or Linux. Please open the terminal window. And once you have opened the terminal window, the first thing we are going to do is to run the image we downloaded a couple of days ago. So for this, in the terminal window, we are going to paste this command, docker run -e, etc. So please copy this command, the entire one, and please paste it on your terminal. Once you paste the command, please click on enter, and then at the bottom, if you successfully pass through, this command, then you're going to see an URL. This URL, the URL at the bottom, will start with 127.0, etc. So please copy that URL.
Felix,
Yes?
let's pause and do a practice. We're going to throw out our first poll here.
Okay.
To see if people, it kind of requires, you know, having the terminal open, having typed that. And I know some people don't have necessarily Docker, the container installed, but we're assuming you have. And I'm also thinking that we could right now, if you don't have the container actually installed, that you could go to a breakout room. Someone can go work with those people separately. So I'm going to suggest, let me just suggest, there's the first breakout room is called container.
Okay.
And if you don't have a container working, I encourage you to actually leave the main room and try to get things going. Hopefully someone else some host can go in there and help, whether it's, I know Amanda's been in the chat, but if you don't have the container working, I'm going to ask that you join that room. And everyone else, if you have this going, I'm going to send a poll question here to say whether you're, if you're trying to go on, if you're ready to move on, you can say yes. And if you're just on Zoom and not, planning to do that, just click yes anyway. So we're going to launch this poll right now, just sort of, so something should pop up on your screen, and just click yes or not. This is kind of.
Yeah, so in this slide you are seeing now, you can see the links for download the image and run the image. So if you haven't downloaded the image yet, so just click on one of these links on the presentation and you will be prompted to the instructions for download if your operative system is Mac, PC, or Linux.
And just to say, this is where you probably want the Google Slides at your fingertips so that you can copy and paste like Felix was doing. And for those of you, we've got 84% are ready to move on, and there's a 10% at 5% at almost or not yet. So we'll wait just a bit longer. And if you're yeah, we don't have any metrics on when we should move on. We're certainly not aiming for 100%, but if we can bring a few more people along, I think we'll keep this whole thing working, keep people for longer. Okay, so I'll just end that poll. We've got we've got a solid number here. And if you're not ready to move on, I would encourage you to join the container, and Julian's in there. Thank you, Julian. And maybe we need some other people for one-on-one. It won't be one-on-one, it'll be sort of collective, but that's okay. There's 5 folks in there. Okay, poll is over, and I won't share the results because that's not. Go ahead, back to you, Felix.
Thank you, Cora. So if for the more than 80% of people that already succeeded in this part, the next step consists of copying the last URL, the last one you got after running the container, and paste it on your favorite browser, and that's enter, and then we are going to be prompted to the Jupyter environment. So this is going to be our main environment where we are going to work during the entire workshop. So our entire workshop is going to be done here. And this URL is going to be accessible unless, or if only if your container is running. So just for making sure that your container is running, if you are a Macintosh or Windows user, you can open the dashboard, which is the graphic interface, and you will see that there is a kind of funny word here with a green icon. So this means that the jovial column is the name of the container is running. The Docker assigns random names to the container, so they can mean nothing or something kind of funny or not, but this word is important because it's one way in which you can identify your container. So in my case, for instance, I have a different container because I already tested this a couple of days ago. And if you already made some tests, perhaps you have more than one container. So it's important to identify the container that you are running currently, because all the progresses you will do in the following steps are going to be saved in the container where you are running now. So for instance, if you run again this command, you are going to create a new container, and all the files that you maybe create in this current container is not going to be available in the new container because each file belongs to the container you create before. So maybe in the future, try to don't get confused creating so many containers unless you want to, and keep in mind the container where you work during the workshop. If you are a Linux user, it's you can use terminal window. So open, if you're a Linux user, you can open a new tab. And the only thing that you need to write is docker ps-a. And then you are going to be listed all the containers you have available in your Docker. So in my case, as I aforementioned to you, I have 2 containers, but it's pretty easy to differentiate between them because the name, jovial column, But for instance, this container is another one that I created a couple of hours ago, 19 hours ago. But this one is the I just have recently created. So if maybe you don't remember the name, maybe the time ago you create your container may give you a hand and try to remember when you create your container. So here in the status, you will see also what is the status of this container. Up status means that this is the container that's currently running. Exit status means that this container is not running. It's up 15 hours ago. It's not working. And a different way of identifying your container is through the container ID. So you can identify your container by the container ID and by the name. So please keep that comment in mind for future consultation about the Docker you are running. So it's important to keep in mind also the URL, because this URL is going to be static. So if by any chance, let's say you made a mistake or you close your tab, maybe no panic, you are not going to lose anything you have done. The only thing that you maybe want to do is just copy this URL, because it's a static, it's going to be the same for all of us, and just paste it again in your URL. And then you are going to have again your environment. This means that the fact of closing your tab doesn't mean that you are closing the container. So it's different. If you close the tab, you are just closing the tab, not closing the container. The container will still be running. This is the basic thing so far. There are a lot of different things you can do in the container, in Docker, basically. And in the extended instructions, you can find them, but they are not relevant so far, so I'm not going to mention. Now I'm going to move forward. If everybody agree and we are fine so far, we are going to move forward for explaining how are the basic features of the Jupyter Live environment we are going to use during the entire workshop. So I'm going to maximize this window. So there are two main things that you need to identify. On the left panel, the left column, you will see your home directory and all the directories available inside your container. These directories belongs to the container and can be accessed from your local machine. So you can only access directly to these directories through your container. In this container, we have two main directories, scope and work. Everything we are going to do is inside the scope directory. We have several directories here that you are going to access each of them during the different steps of the workshop. You just need to click in them for accessing to such directory. Maybe in the future during the workshop, you need to open a file. Let's say you need to open this Python script. You just need to double click on this file, and then a new tab is going to be open in the launcher. This is kind of browser. We're going to have a new tab. And this tab is going to show you the content of your Python script. But it's the same for any text file or any image or any different file that is susceptible to be opened. So if you modify the script, because during further explanation of the workshop, you are going to be prompted to modify the script. Let's say Felix script. And you need to save this script. You can do it by two ways. You can use the keyboard shortcut in the similar way as you do in Word. So Command S or Control S, depending on the operating system you are working with. But you can do it also through the Jupyter environment. So if you click on File and you click then Save Page Python file, then you are going to save your script. So please be sure anytime you are prompted to modify or edit a script during the workshop to save the modifications you have done. You can have here fail and save the Python file. It is possible again to go back to the different directories by clicking on the names, or if you want to go straight to the home directory, you can click here and then you are going to be prompted to the home directory. Also, if you are more fluent with the terminal window, it's possible for you to open a terminal window if you click on the $sign here. So if you click here, you will have the terminal window that is inside the container. So it's important to differentiate between this terminal and this one. This terminal is the terminal of my host machine, and this terminal is the terminal of the container one. So when you are requested to run certain commands during the workshop, unless the host indicates you the opposite, you have to execute the commands in the container terminal, not in your host terminal. Please do it in the container terminal, unless the host indicates you explicitly the opposite. So this terminal works as another terminal with the same command, ls for listing the file you have, cd and the name of the directory if you want to go inside a certain directory. If maybe this terminal is very small for you for seeing it, you can click on settings and you can click on increase terminal font size. And then you are going to have a bigger font size. So like this. So the same comments, ls for listing what you want. If you want to go back, cd dot dot. If let's say if you want to go to scope directory, let's go to scope directory. Let's list the files inside the scope directory. If we want to go to the MTUQ directory, cd MTUQ. And if you want to go to the home directory, just cd and the same comments that you used to use, then the terminal is going to work here mainly. If you also maybe by any chance you want to download any directory, any file from your container to your local machine, the only thing you need to do is right click and download. And then you are going to be, your file in the container is going to be copied and downloaded into your host machine. So, so I have it here. So I have this is the same script, but now it's in my local machine and in the host, not in the container. So if maybe while you run different scripts for MTUQ, you want to download an image, you can do it like this. And there is another several options that are very intuitive, like rename the file, delete it, cut it, copy, duplicate, etc. So these are the main features and the main capabilities of the Jupyter environment. And you are, with these few instructions, you are perfectly capable of moving forward during the workshop. So I'm going to give the lead to Julian for explaining in detail how are the MTUQ files working. So go ahead, Julian.
It's possible that Julian's helping someone in a breakout room. So let me, oh, he's there. Okay.
Okay, so that's this one. So am I on the right slide? So we're gonna see this one. So for day one, we will be using some data that already pre-bundled in the example files that are in the MTUQ GitHub repo. So that's an earthquake for it's the data for the earthquake that occurred Anchorage in April 7, 2009. Well, close to Anchorage. So that's all of the data that you're gonna see if you go to scopes MTUQ data examples and then the ID of the event. And so all of those files are SAC files. So we're gonna have 3 different files for each station with the radial, transverse, and vertical components. So that's gonna be also the kind of assumed orientation of the trace we're gonna use with MTUQ. There's also 2 other files that appear with all of the other, all of the other SAC files, which are the PICs. We're not going to use them. So if I show you, so in these PICs files, there's for each of the station some PNS wave PICs. So there's an option to use this type of arrival time that you might have picked yourself in the code. But otherwise, by default, MTUQ will use the arrival time computed from tau pi relation. So given the 1D model that you'll give it, it will compute on the fly the predicted arrival times. And so the other file is the wait file. So if you've been using Cap or CapUAF, which is the previous code that we've been developed in a group, it's been used to publish several papers. And so it's production level, it's the basis of MTUQ, but in a more modern version now. So this cap file is kind of a legacy format. So it's a text file with several columns. The first one will be the station ID, then the distance from the source to the station. That's going to be used in some computations. There's some option to change the weight of the body weight of the body waves. So for instance, we have 2 columns here for vertical and radial. And so you can see, for instance, that on the Big B station, both vertical and radial component will be used. And if we looked at the surface wave weights, for instance, we'll use only vertical and radial, and the transpose will be discarded. And so you can, if you see that there's a bad trace or just one of the bad signal in one of the particular components, you can rule this one out and it won't be used during the inversion. Also, if you know that you have stations that have kind of low quality, you can put a value different from 0 or 1. You can, for instance, put half, 0.5, something like that, or 0.2 if you go 0.2 if you're really not confident in the station. Here are the 2 columns in which you can put the P and S arrivals. So here by default, we've set everything to 0 because we let the code compute them with TOPI. And those 2 are actually legacy columns that are not used. But they are somehow required if you want to reproduce some of the results from CapUAF by using the same weight file. So all of the previous publications that use CapUAF and that are bundled with supplementary files, with weight files for event, such is the case for Alvisory and Tape 2018 for the North Korean explosions. There are supplementary material with all of the weight files that have been used to perform the inversions. And so you can use them directly in MTUQ. And there's also an option for static correction. So this column is for Rayleigh waves. And so that's basically the default format of CapUAF. So actually, if you want to do static correction for love wave as well, you might want to add another column actually. And so that's it. So that's going to be the 2 main components of the data that you feed into MTUQ. Those are going to be the SAC files and this weight file that determine which station you use, which weight, some of information about the kinematics of your model, the P and S arrival times. And that's pretty much it for me. And we're going to move to the next section, which is actually viewing data download with Bicep, which will be the tool we recommend to download the data. So if Bryant is here,
Yep.
can take it away.
Yes, I've just taken over screen sharing. And yeah, so I'm just going to show everybody some record sections. So we just want to look at the data before we jump into the actual moment tensor stuff. And so we have this kind of adjacent tool called Bicep, which is we'll use in day 2 for data downloading, but within Bicep, we have this record section plotter, which will help us just look at the waveform data. So we have this command here, and then in that slide that we're going to copy and paste into our terminal. And that'll create a record section from all of the waveforms that Julian just looked at. So I'm going to get out of full screen mode here. And copy and paste this command. And so if you want to follow along, I'm just going into the container, opening up my terminal, and pasting in that command that was in the slideshow. It's going very slow. And so this is just changing into that directory that we were probably already in with Julian and running this record section plotter with the SAC files that are in the example data. So you can see some text output coming out just telling us that things are working and we're plotting stations. You're going to see a little runtime warning message that's just bad data that's getting skipped over in the record section, and we're saving our figure as a PNG. Cool. So to find that, we have to go into this directory that we're in. So I think Felix showed you earlier how to navigate through the file system. So I'm just going to go scoped MTUQ data examples. So just click.
Brian, can we pause right here before we
sure.
even go and look for this figure? Let me throw out another poll to see whether this command, and can you type up maybe to show what the command was?
Yeah.
Or
so this is the command that I just ran here.
Okay, I'd like to just see whether people are able to, are
Did that work for you?
ready here. So I'll send a poll right now. And if you think you're in the realm of getting here, definitely write. So let me let's see, create. I'm trying to relaunch the poll. Oops, no, sorry. Kelly, do you mind? When I load polls, I just want to relaunch it. Could you resend it? Or relaunch poll? Sorry, I see it. It's already out there. Thank you. So we've got 80% ready to move on, but we also have 7 folks at the almost level. So if you're in the almost, let's see if it's an issue of, let's see, what do we need to, we need to make sure that at this point, the Docker container has been opened and yeah, Jochen saying have the slides open. You can copy and paste. You definitely don't want to be typing this down from the screen. So make sure you've got the slides open. So but yeah, there's 50 people that are ready to go on. So let's just wait a minute, take a breather, and then and we'll see if we can bring a few more people along.
Yeah, I guess while I'm here, I can just explain this text output. It's on the slide, but this is just a kind of a sanity check to make sure that things are plotting correctly. So it's telling you within our data, just these are just plotting metrics. So like the index within the data, and then the kind of Y value on the plot that we're gonna look at. There's station codes, so showing you network, station, a location, which most of them don't have one, and the channel. So you can see these are in transverse, radial, and vertical components. And then these are source receiver metrics. So the distance, this is now in kilometers, between the source and the receiver, the azimuth and back azimuth, those are in degrees. And any time shift that we apply. So in the next slide, I'm going to show, I'm applying a move out, which would put some time shift on the waveforms to try to align them, and the absolute max value of the waveforms.
Yeah, I think you can move on here. We're definitely going to be watching this sort of 84% metric, and if we see things dropping down, we'll slow down for sure. And if you feel like, we will have breakout rooms open to help at any stage, but we'll probably just kind of keep moving along, and we can bring people back even within. We got a little over an hour here, so go ahead.
Cool. Yeah, like as I was doing before, I'm just going to navigate with the file manager to where this figure has been generated. So I'm going to go scoped, MTUQ, data, and examples. And you can see here, 4 minutes ago, I generated this PNG. It's got this little mountain symbol to show that it's a picture. So if I double click that, I've created this record section. Hopefully everybody's got there and you can see it. You can scroll up and down to look at it. And I'm going to go back to the slides because I just have a breakdown of what this record section looks like. Okay, so this is just like an anatomy of the record section. This is what I was just showing you within the container. Hopefully you all can see it. The orange box is just the title, giving you some information about what's in the record section. So the event origin time, the format of the y-axis labels, which are shown here, like I talked about earlier. And then just some information about like the number of waveforms, the number of events, stations, and what components are there. And you can see that we are sorting by distance. So by default, this is getting distance sorted. So the shortest distance is about like 15 kilometers at the top, and then longest distance is about 200 kilometers at the bottom. And they're all normalized by default to the max amplitude within each waveform. So we can play around with that a little bit also to look at the data in different ways. So here's another command that you can copy and paste into the terminal. I'll do that once I go through these steps, but just to break down what these commands mean. We're doing min and max periods. We're doing a bandpass filter between 10 and 50 seconds. We're going to apply a move out of 4 kilometers per second. And then we're just going to increase the line width so we can see the waveforms a little bit better. So I'm going to, again, get out of full screen. I'm sorry. And copy paste this command. Hopefully you can follow along. I'm going to close this previous PNG file. So just hitting X there, going back into the terminal and pasting. Seems like Zoom slows down my Docker quite a bit. Okay, and we should see, yep, new PNG has popped up seconds ago, so I can just open that up. And here's my new record section. So you can see all the options that we just put in. We've filtered now 10 to 50 seconds. We applied this 4 kilometer per second move out, so we tried to align on the surface waves here. You can see that's kind of pretty good alignment of these kind of peak amplitudes coming in, and then just increase the line width on all the waveforms just so we can see things a little bit better.
Bryant, I just wanted to add here too, this kind of is in the realm of our typical regional distance moment tensor inversion, and where we start cutting out windows and aligning them, it's kind of getting toward the things that we'll be looking at soon. So yeah, and if you're seeing all these funny looking data, well, no surprise there. If you grab data, there's going to be some funny looking things out there. We left them all there. Over.
Yeah, and it's always a good point to look at the waveforms before you start doing any kind of inversion. It's always good to know what the data looks like before you start putting into stuff. And then I just have one last slide. I won't run the command, I'll just show you the output figure, but you're welcome to do the same thing we've been doing before, is copy this command and put it into your terminal in the container. And this is just showing even more options for the record section if you want to play around with this data on your own time or kind of after the workshop. So again, we're doing just filtering, but this time it's minimum period 2, so we're throwing a low pass filter in there. We're sorting by azimuth, so it's kind of useful sometimes to not sort by distance, but to actually sort by the azimuth, so kind of the direction from your event pointing to all the stations. We're scaling here by the global norm, so the largest amplitude waveform that's shown on the record section, and again applying that 4 kilometer per second move out. As Carl mentioned, sometimes it's interesting to look at specific windows. So here we're putting that 75 to 175 second window on there. So we're just looking at these kind of largest amplitude arrivals and only looking at vertical component.
Brian, there was a question about whether this is this displacement or velocity that's being shown?
So PySep was grabbing the data. I think it's in velocity.
Okay. But these have been instrument response corrected.
These have been response corrected, and a little pre-filtering has been done. So in day 2, we're going to use PySep to actually download this data. So we can talk a little bit more about what kind of happens to grab this data before it goes into the inversion. And yeah, if you want to look at more of the options, kind of what you can do with this record section tool, you could just type this into the terminal. It'll give you a help message and tell you what the available options are. Yes, Julian has said these are in velocity, so thanks for the confirmation. Cool, so that's all from me. And I'm going to hand it off to Felix, who's going to talk about running MTUQ.
Okay, let's pause for 1 second. I want to run a poll to see if people made a record section. So going to run a fast poll. So share, relaunch poll. Let us know if you made a record section here. And just while we're waiting a moment here, the question of what to use in the misfit function, whether you use displacements or velocities, is a choice. So I think traditionally we've used displacement, but that can be changed at the time of in the inversion code. All right, this is great. 91% have a record section. So we're going to just end poll, and for the few people who aren't there, we'll try to resolve that in the breakout room soon. Thank you. Go ahead.
Thank you, Carl. Thank you, Ryan. So after Ryan guided us for fetch the data and pre-processing the data and see the data, and maybe at this point in a real life example, you may already review your data, check the station you want to use, the component you want to use for the grid search. Then we are ready for running our first MTUQ example. So please be aware that we have two different examples directories. If you go to the data, we are going to have an example directory. This is the directory where Brian worked. But now we are going to go to a different example directory. This is the examples directory that comes after MTUQ. So the directory is scope MTUQ examples. So please go to the examples directory that comes after MTUQ, not the one inside data, which is the Ryan's one, not this one. This is the one that comes after MTUQ. And here we are going to have some pre-made examples for running different MTUQ grid searches. So please, in the terminal also, go to that directory. So the things I always do is to go to the right cd, enter, go to the home directory, make sure that I'm in the home directory, and then from the home directory, move to the one I want to go. So cd scope, cd MTUQ, again, and cd examples. And here we have different scripts that are already tested and works for running different examples. So there are two different runs in general you can make in MTUQ. You can run for the full moment tensor, and you can run for the double couple moment tensor. In this case, we are going to test the double couple moment tensor at this moment, which means that we are going to grid search for the strike, dip, and rake that best fit the observed data. So the syntax is pretty simple. So the only thing that you need to do in the examples directory is Python grid search double couple .py. In this case, we are going to run an example for a double couple and in serial, because in MTUQ you can also run in parallel the scripts, but so far it's a double couple grid search, so maybe with a serial run we are okay. And these scripts are already made for working with the data that Brian just had preprocessing. So let's enter, and then the first run always is going to take some time, because this example is made for fetching the green functions from the Iris server. So this is nothing to do with the inversion itself, with the grid search itself. It's more related with the fact of finding the appropriate green functions for the stations we are going to use for the grid search. So depending on the velocity of your internet connection, the fetching of the green functions could be faster or slower. So at this point, I think it's going to take a couple of minutes in this stage. So I think it's good now if you can let us know if this command is working for you. Python grid search double couple in the directory of examples, because we are going to stay here a couple of minutes while the green functions.
And I was just going to add that I'm going to email. Iris knows that we're going to hit them with this request from 50 or so people potentially. So we don't know exactly what will happen here, but there's certain reminder that fetching waveforms is not always reproducible. You know, if you try to fetch batches of waveforms from Iris or synthetics, that's not guaranteed to work all the time. But you're looking at it in live, and probably this is slower. So this is just to reiterate. Yeah, it's grabbing AxiSem, InstaSize, Syngen, synthetics for a 1D Earth model to run this. We're not calculating them locally here. We're fetching them.
So I would like to add that this information you see here, reading data and preprocessing data, this preprocessing is an MTUQ preprocess. So the filter you saw with Brian's example, it's only for purpose of observing your data, but inside the scripts, you will learn in the day to how to change the filter you want to use for making your own research. So we already read the data, we preprocess the data, and now we are reading the green functions, which means that the green functions are being downloaded and then reading and preprocessed as well.
Go ahead, Marta, question?
Yes, sorry, I don't understand. Why would you say that the fetched synthetics would not be reproducible from Iris?
Yes, sometimes when you make a request to fetch data or anything from a data center, there can be problems. Yeah. I mean, you would hope that the synthetics, when you get them, they should be what you expect, but anytime you make a data call, you hope it works, but it doesn't necessarily always work out. Is anyone else experienced that? It's just maybe it's like 95 or 99% of the time, but sometimes it just won't. There'll be some break in that connection.
Right, okay, but it's not that, you know, our downloaded synthetics are not the same. That's reproducible.
Correct.
In the sense that this should, okay, fine.
The command being reproduced, like when I execute this command, I expect to get back this, and that doesn't happen. That's what I meant. Good point.
Okay, thanks.
Yeah, you only just have to point out something very important, since don't know if the green function depends on your internet connection. It may happen that during the process you have bad luck, as sometimes I have, and the process of downloading the green functions are interrupted because of your internet connection. So if this happens, maybe we're going to have an error while you're trying to run the grid search. It's an error that has a message like that zip file error. This error means that MTUQ thinks that the green function is there because the file actually exists, but the file is kind of incomplete or broken, but the name of the file, the green functions, has been created in the directory where the green functions are stored once you don't know them. That's why you have this error. If you have this error, the rapid solution is to remove the files in the directory where the green functions are stored, which is here. But please don't use this command if you don't have any issue downloading the green function. So this is a command for being done only if it's completely necessary when you have this bad zip file error. Otherwise, you don't need to do it at all, because you are going to delete all the green functions if you use this command. It's also possible that the computer let you know that you don't have a good internet connection for downloading the green functions, and we're going to have an error kind of connection timeout. If this happens to you, just try to find a more stable internet connection and try it again.
Felix, how does this compare with Zoom running and the container running? How are these speeds compared to what you had without those?
Sorry, I missed you. Carl, can you repeat, please?
I was just wondering if this was relatively slow for you compared to not having Zoom in the container, or is this? I mean,
no. I mean, it didn't make any difference to me. Not significant. I
okay.
tested with Zoom already, and now I mean, it might not affect too much your performance. But of course, it may vary from a computer to another. So now we have the green functions, and now we are moving forward with the grid search itself. So the grid search start once you see the measures evaluating when you test it, which means that the system is moving forward with the grid search.
Okay, let's pause here, because this is where probably, you know, a lot of things could either take long, or we're getting to the stage where things could kind of go haywire. So I'm going to launch a poll and probably relaunch it once we see where people are. But maybe the question is, I guess yes here would mean you've actually finished this command, and not yet or almost, something in between. Almost would mean it's running, say, and not yet is some other issue. So here comes the poll. Okay, so we've got, it's looking pretty good. About 75% yes, 23% almost. So that suggests things are running. So we definitely want to wait. If things are running, wait for those to finish up. Can someone, can you, after you submit your poll, can you change your answer if you go from an almost to a yes? I don't, maybe not. Oh, there's good questions going on about local AxiSem databases. Definitely, yeah. That's a bigger topic, but you can generate your own AxiSem databases for local or global version of an Earth model, a 1D Earth model. Okay, I kind of feel like, is there anything else we want to cover here? I think we can just go on. We have 70% at yes when they submitted the poll, and a quarter almost. You know what? Bear with me, guys. Let's just launch one more poll here and see if we can get that number up. And yeah, we'll end this one and relaunch one more time. So once more, quick answer and see where we are. Here it's coming your way. Okay, it's over 90%. So for the almost, it'll pick up here. And frankly, if you're already at this stage, you've already completely run the code with the data. So you're doing a great job. We're happy to see that. Go ahead, Felix.
Yeah, I would like to address a question that Laura is asking. So how many green functions are there? It is a very good question. It depends on how do you set the parameters of your grid search. In this case, we, as fast as possible, we fix the depth of the earthquake. So we are going only to grid search over the strike event rate, which means that we are going to allow a single set of green functions for each station. The distance between the epicenter and the station itself. We don't allow for different depths, or only for the depth of the earthquake, because we are not grid searching over the depth of the earthquake. But if you want to grid search over the depth, then you are going to have more and more green functions. But it's important to know that the downloading the green functions takes time only, of course, the first time you run the event, because once you try to make different runs, you already have the green functions. So this is just a thing or an issue of the first time you run your example. Because if you modify certain parameters of the grid search and you try to run again, you don't need to download the green functions again, unless of course you add more stations. Yes, so the first one is the one that takes more time. So once you have passed through the entire process and you are ready to finish it, you can identify your output files starting by the name 2019, which is the date and the hour of the earthquake, the letter DC, which means double couple, underscore, and then beach ball, misfit, etc. So if you make an ls and 2009, sorry, and here, then you are going to see all the files that are the output of your grid search. Among all these files, the most important are the pitch wall, misfit, and waveform. So if you click on them, you are going to be able to open it and see them. And these files summarize the outcome of the grid search. And I'm going to pass the lead to Julian for explaining thoroughly how to read and interpret those files. Go ahead, Julian.
Unmute, Julian.
Sorry about that. Someone asked in the chat where are the greens functions stored. So they will be in the data greens tensor and Syngin, because we've downloaded data from Syngin, in this cache folder. And if you actually open one of them, you'll see that you have all of the SAC files for all of the greens function that we are using, plus a log file. And in general, we keep all of the zip files used for the download during the download, just in case we might have some corrupted data at some point. So that's just to be on the safe side. So let me go to the slide. So now that we've generated a couple of figures from Felix's example, we're gonna have a look at the waveform data that you've generated. And so these waveform data contain a bunch of information, which most of the important and relevant information are actually in the header. So you'll have the origin time used to download the greens function. So the greens function will have this starting time minus some buffer for this latitude and longitude of the event. That's the magnitude inverted for. So here we haven't inverted magnitude, so that's the magnitude we told MTUQ to use, and that's the depth that's also been used to download the greens function. Here we are working with AK135 2-second model, which is the global one downloaded from Syngin. Here's the L2 misfit value. So that's actually something interesting to look at if, for instance, you do a couple of runs and you want to compare them. Looking at the absolute misfit value might tell you if you have got a better result in terms of data fit. Here are some parameters that have been used for the inversion. So the body waves are filtered between 3 and 10 seconds, and we are using a 15-second time window. So here is only 15 seconds worth of data. And the surface wave have been filtered between 16 seconds and 40 seconds, and we have a 150-second time window. So those would be a typical value that you can use. But if you are working with like a longer distance and potentially longer wave train, you might want to increase the number of samples for your surface wave time window, and adapt for the body wave as well if you need to change a bit for the filtering. And these are the results for the moment tensor. So we have strike, dip, slip angles, and the loon coordinates, which here, because we are working on a double couple example, are 0, 0. So if you remember the figure of the loon on the loon, it's the center of the football, which is for a double couple. So on black, we have the observed data, so the SAC file that we've loaded, and on red, we have the greens function combined with this specific moment tensor, which gives you the synthetic observations, and we can appreciate the data fit. And underneath each of the trace, we're going to have those 3 numbers, which are the time shift in seconds. So for this, all of this one, we have allowed a time shift actually to be able to position correctly all of the traces together. So for the body wave here, it was plus or minus 2 seconds. And for the Rayleigh wave and love wave, it was for plus or minus 10 seconds. So you see that the arrival times were not too far off, the one predicted by using the tau p method from the 1D model. Then we have the correlation coefficient, which is also an important metric to see whether the data fit is good or not. And then the bottom one would be the total misfit contribution in percentage for all of the traces. Then if you go on the container and you open this file, the double couple misfit, you'll be greeted with these 3 figures, which represent the misfits in the 3-dimensional space that we've probed. So we've explored the strike, dip, and rake angle here. And so these are the 3 maps that basically tell us that the solution is here. And so in theory, we have 202, 47, and minus 83. And so that's the result we have here. So minus 83 slip. The dip is about the 47. So it's close to here. And then the strike, which is at above 202, which is at this point here. And so this representation is actually 3 slices into the 3-dimensional space that we've searched. So here I have just a little sketch representing how we measure the misfit for each grid point. So here, let's imagine that we look at 3 different strike value, 3 different dip value, and 3 different slip value. We're going to test all of the different combination of them. So we're going to have in total 3 by 3 by 3. And for instance, this map, the stripe and dip map, is only the slice here that correspond for the minimum slip value. So the minimum misfit is given for this slip value, and then we just look at the map here. And it will be the same for the strike and slip. We only show the map where the dip value gives the minimum, and the same for this one. So we've looked at 40 to the power 3 grid points, and here we're only displaying a tiny portion of that. So that's also something to keep in mind. What the actual misfit space is much larger than the few figures that we are showing, but these are the ones that we are caring about. And you can also see that because of the strike is something that rotates between 0 and 360, there's actually a repeating pattern that generally occurs when you do when you look at this type of figures. So now we're gonna move. Are we ready to move on? Carl, do you want to launch a poll to see if there's some questions about the
Yeah,
input
good
commands?
idea. Let's I guess well, I was in the chat. So were there commands that needed to be executed, or should I just say are
Not
people
yet. It's just if there's any questions.
any
well, I can
questions? Yeah, just raise your
while you're
hand
doing
if you
that.
have questions. There's a lot going on in the chat and a lot of
Okay.
stuff that we would plan to dive into tomorrow. So we certainly hope to pique your interest enough to show up tomorrow. But yeah, feel free to
So if
raise
not,
your
we
hand.
can continue. So back to the terminal, we are supposed to be in scoped MTUQ example, and we're gonna do the MPI run n equal 4, which is the number of processor we're gonna use, Python grid search for moment tensor.py. So if you have more than 4 cores, usually Docker might not be using the full extent of your machine. So 4 is a good safe bet for using this command, and it shouldn't crash anyway. So it's gonna run. So I don't have all of the outputs out, but we've done opening the data, processing the data. We've read the green function, and then we do the misfit computation. If you want to have all of the information printed out when we run the MPI run commands, you would have to add, let's see, you would need to run this command instead with adding this here. So I hope you don't hear the fan noise of my computer. It's getting pretty loud. Can you still hear me?
Yeah, we
Okay, good.
We were commenting that, yeah, once you may have some cores on your machine, but once
Yes.
Docker is occupied, there's some unknowns here.
CPU temperature is about 86 degrees now, so everything is running perfectly. And so now we have new figures that have been generated. So now we don't have the double couple.
Okay, pause for a second, Julian.
Yes.
Let's launch another poll here. So the goal here was to first, if you look, to make sure you're in the right directory, this /scope/MTUQ/examples, and then that command. Can you just press your up arrow to find the command, or scroll?
Yes. So it will be MPI run n, the number of process on which you want to run, Python, then u, and grid search full moment tensor.
So if it has executed, say yes. If you've at least launched the command, say almost. And here comes a poll. Okay, we're definitely going to wait here. We've got 60% are done. That's great. 40% almost. So that's great. Thank you guys for sticking in this. So we'll wait a few minutes here. What are some topics related here? Maybe
I'll comment on why it's taking actually longer. Because on the other example, as you see, we only had 6.4 to the power 10 to the power 10 to the power 4 points, because we were using a grid search for 40 points, 40 angles for strike, dip, and rake. And for this example, we have added 2 dimensions, which are the Lune coordinates. And so if we look at, so I don't remember exactly the number of points for this grid search, but we have 10. So we're going to have 10 by 10 times 2, and then 10 to the power cube, which gives us this number of grid points, which is an order of magnitude greater than the previous one. So it should take roughly about 10 times more than for the double couple search.
Julian, could you comment just to sort of open up people's minds a little to this capability? What were the max grid points you were running for these MPI Tonga event?
So for the MPI Tonga events that I done recently, we had 10 to the power, a bit more than 10 to the power 9 grid points. And it actually crashed once I go a bit further beyond that, but it was mostly because of the plotting tools. So I need to figure that out. But otherwise, I haven't seen any limit in the number of grid points, at least to perform the grid search. So potentially another magnitude above that.
We're going to relaunch the poll here. So see if more people have finished here. Please answer on this one to see whether it's finished. Okay, so for the almost, we're moving along, but we're at 75%, 20%. So I assume almost means things are running, but we all have different, different machines here. We had, just as an aside, we had an option to sort of run this whole thing in Amazon Web Services, whereby we're all with the exact same resources, but our feeling was that people would prefer to at least run this on their own machines, have something in hand. But it's something we thought about. We could probably guarantee that these things would all work if we're all running from some AWS Jupyter Hub platform. But these choices are changing as we look at these kinds of training opportunities. So we're at 77%, 18%. I think it's worth waiting a little bit here still.
So there's a couple of questions in the chat.
Okay.
So the U for MPI run will simply give you interactive output instead of printing everything at the end of the runtime. So it's a bit better if you want to check what's happening while the code is running, and otherwise everything will be printed out at the end. So here, do this. For instance, you see here I didn't use the U option, so it only display the progress during the grid search, and it actually outputted the rest of all of the prints at the end. Then can you be so unlucky that if you refine your grid significantly, you get a different result? Absolutely. Because basically what's happening with the grid search is that, for instance, here we are only looking at a couple of degrees. We have 10 degrees in each direction. So if the global minimum is somehow in between 2 points, well, you'll never be able to find it. But the further we add grid points, the smoother the solution tends to be, and it's not very often that you'll see a dramatic change in the solution. You'll just refine the estimate, basically. So for these type of maps, for instance, it would make just everything be a lot more smoother. So I can actually show you. We're doing a bit of extra work. Do you typically do some sort of grid refinement? Yeah, it's usually better to start with a low number of grid points just to see to have an idea of what the misfit will be looking like. And then if you suspect that with some refinements, you're gonna change the shape of the misfit a lot, it's gonna be better to increase the number of grid points. And using a coarse grid will potentially help you at first tuning the different parameters for the filtering. For instance, you could be changing the pre-processing of the data. So how much do you filter, which frequency band? You might want also to be playing with the length of your time windows, the allowable time shifts. So all that can affect the solution of the inversion. And so first, using a coarse grid will save you a lot of time doing this. And so if now we look at the...
I wanted to just add to Julian the motivation of other search methods besides just coarsening, but Julian will be kind of hitting that tomorrow, these different approaches to searching the space. We're at 90%. Thanks, everyone, on who responded to the poll, or if you're, it might have just come up for you above 90%. So we'll take that as an A-, move on.
Yes, so I realize we haven't dedicated some time to look at what the code is looking like. So that's one of the scripts to run the double couple grid search. So at the beginning of the script, you have the typical Python import. So we're opening most of the tools we need from MTUQ. That's to, well, that's the intro. We won't really pay attention to that. So here we're going to give some paths. So here we're going to look at the data example. So that's where are the SAC file located in the MTUQ folder. So that's the file we've been looking at a bit previously during the workshop. Here it's the weight file. So full path here is actually searching within the MTUQ folder. Here's the name of the model we're using. And so here we first define the pre-processing, so all the filtering. So for the body wave and surface wave, we're using different type of processing. So two bandpass filter, but with different frequency. For both, the peak type will be automatic. But for instance, if you have very fine P wave picking, you could here use user supplied instead of tau P. There's some tags that are useful for the processing at the end, and the path weights tells us which station to use or not to use, which components to use or not to use during the inversion. Then for both, we define also the misfits. The misfit could be different for body wave and surface wave. So for instance, we have two implemented misfit measures, so the least square norm and a hybrid between L1 and an L2 norm. And then we define the grid, which is the kind of the third component we need. So we'll first have the data, the grids function. So for the grid, we have a function that's called double couple grid regular, which only takes two arguments, the number of grid points and the magnitude. So magnitude could be a list. For instance, if you do this, it will search over these two magnitudes. So you have a total of 90 times 90 times 90 times 2 grid points. Then there's a couple of other more parameters of the origin. So we predefine everything at the beginning. So where to fetch the data, how to process them. Then we actually open them. Once the data are opened, the code will figure out which greens function to download. So it will download them from Syngin here with download greens tensor. It will pre-process them, scatter them through across the processes if you are using MPI. And then you'll just compute the results by doing the grid search. So you open the data, you load the grid function, you define a grid, and then you perform the grid search. And there's a couple of other ingredients like the misfit, the origin time. You could have an origin time list as well, which would further increase the number of grid points you'll be evaluating. And so that's it. But we'll be a bit more in detail about this information tomorrow, where we'll actually ask you to modify some of the scripts to do depth search, for instance, or magnitude search.
What stage is it at for you, Julian?
Shall we continue? Yes. So here I'm just showing a quick example of why we want to use parallel processing. Well, it's simply that if, for instance, I were to rerun both this example with only one processor, it would take about 20 seconds to evaluate the body wave and 150 for the surface wave. While if I'm using 4 cores, well, it almost scales linearly because we are simply cutting the grid space in and doing an equal repartition being each of the processors, each of the cores we are using, or each of the processor in case of an application on an HPC structure. So it should scale about linearly, which is about that if you look at the number here. And so these are the figures that you get once you do the full moment tensor grid search. So on top of the strike, deep, and rake figures that you could generate, we would typically also look at the loon plot, which displays the misfit on the depending on the loon parameters. Here we can also see how much the moment tensor solution has changed from the double couple test that Felix showed us previously. And again, we'll have the waveform fits plotted. And so if we look a bit closely at like how this figure is computed, well, this one is a bit more complicated because it's not a simple slice through a 3D view. Here we have only one surface to look at, and it's actually an aggregation of all of the best fitting moment tensor for each of the coordinates on the loon. So if we look at this version of the map here, which shows the trade-offs between the loon coordinate, which are basically the latitude and longitude along the loon, you'll see that, for instance, those two moment tensor are actually quite different in strike deep and rake, or strike peak and slip angles. And this is just because the way we are computing this figure, for each of these moment tensor location, we'll take all of the best values, we take the misfit values for this location, and then we plot the misfit. And so you can see that the best fitting moment tensor is actually quite far from the double couple solution if you look at the distance along the loon. And I think that takes you about the end of today's session. There are a couple of other instructions that you might want to look at. So I think some of them are related to Docker.
We don't need to direct people to the extra, yeah.
Okay.
But I will, maybe Julian, could you show that last slide and we could just sort of scientifically go on a couple items. So did you show where these figures reside in your local directory? Just to see whether people can find these and that they ran.
So we haven't generated this one. This one is
Okay.
just for an example.
Okay.
But here we have all of the figures. So that's the FMT waveforms would be the waveform fit figure.
Okay.
FMT misfits will plot the misfit on the loon, and the FMT beach ball will plot the beach ball with all of the stations per scene points.
Could you go back to the slide too? I just wanted to kind of mention in the beginning we were saying that uncertainties are large. So when you look at this solution beach ball that Julian, maybe you go up one to show what this beach ball looks. Yeah, I mean that looks very, very different from the double couple, best fitting double couple. So these are cases where we're not saying that this is definitely an exotic solution, but that is what the actual waveforms and the program is showing you is the best fitting beach ball. There's other information. For example, you might bring in polarity data, which we haven't talked about. You can see that these would all predict the same polarity, and that constraint might really help you sharpen this. But the figure in the middle would not be surprising if you took any given earthquake. I think people kind of expect that it's going to fall right on the double couple. But in fact, the waveform suggests that quite a large range of possible solutions exists, especially when you think about, using a 1D model or not using polarity. So I think that is the set of slides we have. Julian, could you leave it up on the final slide? And we don't want people to leave quite yet. We had sort of like 20 minutes left of this time. And there is, if you do have to leave, we would greatly appreciate it if you could fill out this survey. For us, we would like to know kind of where people got, and you could fill it out anytime you can, if you're in the slides, you can find this. We would just like to know what we can do better, what you'd like to see. Keep in mind that we have a 4-hour session tomorrow. We're really going to dive in, but we figure some people just want to dip their toes in the water here and see what this is about. So please, even if you didn't run the container at all, please fill out the link and just say, that question will say, I didn't run the container, but I participated. We'd like to know who you are and whether you want to be on an email list. So we'll send this around as well later, but let's just open up to any questions of any kind. And we can, if there are, I was checking the breakout rooms. It doesn't look like anyone's in breakout rooms, but we'd like to help everyone along here to get to the level where we come in tomorrow and there's kind of more science and exploration of these codes, a lot of questions and experts I know from the chat here. So any questions right now? Yeah, go ahead, Marta.
Sorry, so my question will be quite simple, but I'm not an expert on moment tensor solutions at all. Could you sort of talk about this trade-off a little bit more? Like, what does the plot actually show? And then how do I then say, which solutions are equally likely or something like this? I mean, because I don't really understand that loon figure so well to tell me,
Yeah, can you go to that slide, Julian? I will start and then hand off. But what I would say is part of our goal is just visualization. We don't in my slides in the beginning, I showed this gallery of all kinds of stuff that quantify different kinds of, a probability density function for source type, for example, that could give you information specific to the source type. Here, it's really a starting point for visualizing what's going on. And you're right, it doesn't tell you exactly what trade-offs are, but the information, because we evaluate the entire space, and let's consider also, say, depth and magnitude variations. So at each point on the loon, there's also, variability in magnitude, there's variability in depth. Heck, you could even have location. So there's a lot of other information, and we're showing the best fitting moment tensor lowest misfit value over all of those. So it's a starting point for visualization, but I would say that, generating, say, a set of 1,000 samples of this posterior that have all these coordinates, we can do that. I mean, we don't do that as part of the code, but once you have 1,000 moment tensors that are representative of your solution, you can imagine answering the statistical questions that you want to. Because if you have 1,000 representative, you can plot, well, how does strike vary against depth? Or how does the magnitude vary against the source type isotropic component? That sort of samples of the posterior enable statistical questions to be answered very easily. It's not directly part of the package, but that's really a capability. So maybe, Julian, you want to expand or a foreshadow for a CMA, yes, or anything?
Yeah, so that's also something that so the difference between like any kind of like Bayesian inversion framework, or if you were using only a probability density function as an outcome, is that here we actually try to sample the misfit the more extensively as possible. So we kind of have a full representation of the solution space, which in a way gives you different type of information than just having, for instance, the variance over the strike or depth. It's a bit more complex to look at this type of information. So that's also why we are looking forward to implementing other methods based on stochastic sampling to basically increase the possibilities we have with the code. So instead of having a full presentation of the misfit, we would be sampling where the low misfit is, because that's kind of the information that we're interested in. And potentially then you could have some Gaussian posterior, which will give you the shape of the minimum misfit. So here it's actually very important to look at kind of the overall shape of the misfit. So I'm going to show you what, for instance, a typical explosion would look like. For instance, can I, damn. I lost the cursor in between my two screens. Okay. No. So that's, for instance, the loon plot that we generated for a study of the Tonga eruption from January 2022. And this is the type of misfit figure that you kind of expect for explosions, where you're going to have mostly here. You're going to have mostly moment tensor in this swath of low misfit. You're going to have mostly moment tensor with a black rim at the edges. And this is due mostly because we have an explosive source at the surface, and it's very difficult to find the source type because of that, because basically having this shallow source that will radiate the energy the same way if it's here in the misfits or along this swath of low misfit value, that's kind of complicated. So we've used this, looking at this misfit is what actually gave us a clue that the Tonga eruption actually was a huge explosion. And we also started to look at the numerous trade-off you might have between the loon coordinates and the moment magnitude here, which is the map you see here. Let me try to zoom in. So you see that we have very complex pattern that are kind of centered around this differentiation between the positive eigenvalue and what you would have here with the negative ones. And same goes with the depth and the moment, depth and the location on the loon. There's also complex trade-offs. So it's something that we need to keep in mind when we are doing moment tensor inversion, is that it's not because you get one solution that's that the solution that you get is actually representative of like some Gaussian statistics. So it's I would be very cautious with giving only like a standard deviation of any given value from all of the parameters we are testing. And here we have how the misfit actually varies with depth, and also the source type plot varies with depth. So you can also see that there's trade-offs between magnitude, depth, and also the source type here. The source type is different if you look at 0 kilometer depth, for instance. So that's kind of the takeaway message, is that the misfit is complex. It might not be unimodal. It might not be quadratic. And so having this sort of representation and visualization capability is actually very important for us, because we want to be able to see those trade-offs and assess the quality of the result with that.
Yeah, those are great points there. I was just going to allude to the simpler in the past. Well, it's possible that we could deliver something like samples of the posterior. It can be done for smaller. It's been done for smaller problems as a way to kind of hand someone a more distilled version. But it is challenging to say, if someone wants one number to represent the solution, it's hard to deliver that, but we can, as long as we're clear what kind of statement we're making or when we deliver that. The chat is on fire. That's great.
So I saw that there's a couple of complaints about the potential Apple Silicon chip. If you got a brand new Mac and trying to run on Docker. So if you see here, I have my trusty Windows logo because I had to give up on my Mac. It took me a bit more than half an hour yesterday to run one of the example. So there's clearly a problem with Docker here. At least I've been able to replicate it. The program actually runs very fine on the M1 chip. So if for tomorrow you want to try installing it directly on your machine using just your Python environment in Anaconda, we can also try to add some additional instructions to install MTUQ on your machine.
That's a great idea.
That might help us for day 2. It shouldn't take too long. It's about maybe 15 minutes for the complete installation. What long period? 25 to 70 seconds.
Yeah, so if there's any questions in particular, if you're on the fence of coming tomorrow, any questions that would push you toward coming tomorrow. And in terms of what Julian said, like if you've got the Apple chip, you know, we provide the install commands for, and Ian was able to make these containers, but those same commands should work without the container. We're just trying to simplify that, that process.
So about the source time function, so it's actually the first time we've tried that. It was for the Tonga eruption, because it's been kind of clear that there's been several events happening in a short succession. So over the span of a couple of 100 seconds, we have been able to identify four sub-events, sorry. And when using those four sub-events with MTUQ, we've been able to fit the first pulse of data, which correspond to the first explosions, and then secondary information. So that's the thing that are like available in the code. Is just a matter of estimating a source time function and convolving your Green's tensors with it, and then you'd be able to get to either have one complex rupture represented by one source type. And for this case, we've made the hypothesis that we had 4 repeating explosions. Otherwise, you might want to invert for more than one moment tensor solution, which we haven't tried yet, but it's supposed to be possible. The code is actually very, very flexible.
Well, can you maybe put up that last slide about the survey and drop that? I'll drop the link in the chat as well, just so that, yeah, just to make it, if people are leaving right now. And I think, is there anything that we're missing? I should call that survey. Here we go. Go ahead, Dorian.
Hi, just a quick question. For tomorrow, when we're gonna log back onto Docker,
Yes.
do we use again our terminal and write a new, like the same line, the long line with and we get our website, your URL, or we can use the same URL that we use today?
Felix, you want to field that?
I'm not sure if I was clear. I'm sorry.
Yeah.
Sorry, I was running some examples and I have a problem that in my computer, my microphone and my headphones are, the inbuilt speakers are next to the fan. So when the computer fan starts working, I cannot hear properly. So would you mind repeating, please?
Yeah, so I'm just wondering for tomorrow, do we just copy paste the same URL than today on our browser?
Yeah, you can.
Or...
Yeah, I'm going to share my screen now. Yes, the same URL. It should work because it's the same for us, because maybe I didn't explain. Actually, didn't. But when you run the container, you define a port in your computer to attach a port to your computer for running the container. So this URL is going to be always the same. So if you copy it and paste it, it should guide you through your environment again, if only if, of course, your container is running. If your container is not running, then you are not going to be able to move forward. But if you look at the hidden slides, I put there some instructions for restart the container. So maybe you're going to take rest now. After lunch, you turn off your computer and you restart again Docker, and you want to restart your container because you don't want to create a new fresh container. You want to keep working in the same space you already create today. So here you may find the instructions for restart the container and how to turn off the container as well. In some cases, maybe
Felix,
somebody of you.
I just want to make sure there's more, probably more information than they need. I mean, if she opens a terminal and starts from scratch with that Docker run, copy and paste, is that okay? Or, I
Yeah,
mean,
yeah, it's
okay.
that okay. Yeah, if you just run, you are going to create a new container different from the one we create today. And you paste the URL, then you are done and you are ready for keep working. But keep in mind that if you do this from the run from scratch, you are going to create a new container. So
Okay.
everything you have done today is not going to be there because it's going to be in the container you created today.
Let's just make sure for day 2 that we go over that in the beginning, I think, for tomorrow. Okay,
Thank you.
we're winding down. I think we may try to exit here before the 2-hour mark. If there are no other questions, we still have 60 or so people there. And yeah, we really, thanks for the host team here and for everyone for showing up. And please, yeah, please join us tomorrow. There's no obligation to come for 4 hours. You can come for whatever you're interested in. And we'd be interested to hear a lot of suggestions here about what we can think about with regard to future developments. And we'll be talking about that too. Any last words from anyone here on the team? Okay, thanks everyone. Bye.